Okay, in this segment, we're going to talk about a little bit more of this idea of a heat of a reaction. But instead of talking about it in terms of a chemical reaction, we're going to talk about it in terms of something dissolving into solution. Okay? We already learned earlier this year that when things dissolve into solution, that they can warm up or they can kind of cool down. At that point, we just kind of noted it. We didn't do anything with it. Now it's time for us to put some math with that. Okay? So just like a chemical reaction, where if you put two chemicals together and they form new chemical bonds, that creates an energy change. Same thing happens when you dissolve something into solution, okay? Sometimes when you dissolve things into solution, they release heat energy. Sometimes when you dissolve things into solution, they absorb heat energy. So we do have both endothermic or exothermic heats of solution. Notice how our symbol here is exactly the same as before, but now it's just our delta H for enthalpy change, and now we use a little S for solution instead of RXN for reaction, okay? And we can track it and do the math the exact same way as we've done before. Now, a couple of different examples of that. There's one way you can actually get a chemical hot pack. These are not the disposable, like powdery ones that you maybe get at the gas station. These are nicer ones that you maybe would use in a medical kind of kit that you actually could crack open and it would generate heat in those kind of scenarios. In those kits, what they have is they basically have water and solid calcium chloride in two different pockets. And when you crack them open and squish them together, that calcium chloride dissolves. And as calcium chloride dissolves, it produces extra heat energy. So the process of breaking this apart absorbs a little bit of energy, but then the dissolving and bringing them into their solution state then releases a lot of heat energy. And our net change is 81.74 kilojoules per mole of calcium chloride dissolved. So that is an exothermic process when then we enjoy that. Another cold pack, we've talked about other cold packs before, but you can actually take just ammonium nitrate and dissolve it into water, and it also will get very cold to the touch because it's pulling heat energy from the surroundings because it has to absorb 25.7 kilojoules of energy to allow it to dissolve. So that's an endothermic example, okay? Little side note, like hand warmers that are mostly solid, those are actually a chemical reaction called the oxidation of iron, but they're more of a chemical reaction. That would be a heat of reaction. And those self-heating meals that you maybe have heard of before, you can get those at like outdoor stores or the old MRE military meals. They are similar, but they're an oxidation of magnesium, which is even more aggressive and gets hotter. Again, that's a chemical reaction or a single displacement or single replacement of magnesium. So all of these things are using the concepts of thermochemistry to use for products, that kind of stuff, okay? So let's take a look at one of these examples here, and let's just take the first one, the calcium chloride example, and let's say we want to dissolve 25 grams of it, all right? So if I have my calcium chloride solid here, and I'm going to react that to make my calcium ions plus my chlorine ions, I'm going to need to have two of these guys. And we're going to make or produce 81.74 kilojoules of energy off that. So if I dissolve 25 grams of my calcium chloride, the question is, how much energy would I get out of this? So we'll do the math exactly the same way that we would have done for heats of reaction. So I'm going to somehow convert these 25 grams into kilojoules in a little stoichiometry. Okay. Now our first step is, of course, to go from grams to moles for our calcium chloride. So we need to figure out what the molar mass is of calcium chloride. And then our next step is to do our mole ratio. So we know that for every 1 mole of my calcium chloride, I'm going to make 81.74 kilojoules of energy. Okay? And then that's pretty much it, right? That's our process. I can now say if I dissolve 25 grams of calcium chloride, I can now make X number of kilojoules of heat energy being released. Now, for a manufacturer, that might be important because they want to put the right amount of calcium chloride in there to produce the right amount of heat energy. They don't really want it to get too hot and potentially burn a person, but they want it to get hot enough so it's actually usable for them. So let's take calcium here, and let's get its molar mass. And calcium is 40.08, so we got 40.08. Plus 2 chlorines, which would be 70.90, and we get a molar mass of 110.98 grams per mole. All right, so I'm going to take that, and I'm going to take 25 divided by that number, and I'm going to take it times my 81.74, and I get 18.413, or to, let's say, let's just call it 2 significant figures. So that releases 18 kilojoules of energy. Now, because it's exothermic, my change in enthalpy would be a negative 18 kilojoules, because this is a negative value inside here. So make sure that you identify that negative in your math, okay? Notice how the math I did today is no different than what we did for heats of reaction. It's just applying it to dissolving things into solution versus a heat of reaction. All right, thank you.